allocation schemes. Okay, so do you still remember? So how many memory allocation schemes that you have learned in this chapter? Ada berapa?
4.
Okay, 4. Mana yang lain ni? Where are the others? Tak dengar suara. Okay. Okay, so there are 4 allocation schemes. Okay, in this chapter. Okay, you learned about page allocation. Okay, demand paging allocations, segmented allocation, and also segmented or demand page allocations. Okay, so so these are the 4 schemes that you learned in this chapter. All right, so the purpose of these schemes, okay, being introduced is trying to remove this restriction of storing programs contiguously. So if you remember what you have learned in chapter 1 and 2, okay, there are some restrictions in the previous development of operating system, okay, where the programs need to be stored contiguously. All right, so in order to remove that restrictions, okay, in the previous development, okay, so they introduced these schemes, these 4 memory allocation schemes. So the page demand, segmented, and segmented demand page allocations. All right, so this will actually help to eliminate, okay, the requirement that the entire program resides in memory during executions. So we don't need that entire programs to reside on the memory during the executions. So it's more practical, more efficient, okay, when you want to run the programs. Okay. So some terms that you need to understand about this, okay, so sector block and then page frame, so you will see these terms continuously in all the chapters, okay, and then so in page, sorry, is there any question? No. Okay, so in page memory allocation, the first scheme, okay, so all incoming job is divided into pages of equal size. So the keywords here is pages of equal size, meaning that when you have a programs, these programs will be divided into pages of equal size. So you actually trying to remove the drawbacks of having internal fragmentations, right? Sorry, not internal, external fragmentations. So for this, okay, for efficiency, pages, sectors, and page frames are of the same size. So it means that it's easy to handle everything. So let's say you have a job of, let's say, 240 kilobytes, okay, so you can set to divide the job into, let's say you want to have 4 pages, so each pages is going to have 60 kilobyte of size, right? Okay, so that's how it works. Okay, but probably, okay, that if you have the exact amount of the size, I mean, for each pages, so they probably have, let's say you have let's say 250 kilobyte of size. So when you divide it into 4 pages, okay, sorry, 4 pages, is it 4? 5 pages. You need to, let's say you need to divide into 60 kilobyte size of page. So it means that you're going to have like 5 pages, right? So, and the last page is going to have only how much? 240, 250. So you're going to have 10 kilobytes for the last page. Okay, so that is one drawbacks of this scheme, which means that you're going to have an internal fragmentations, but only for the last page for that one. Okay, so it's still practical to be implemented. Okay, so that's for page memory allocations. Okay, so this is how it works. I think you can actually read through this one. Okay, The good thing is that you don't need compactions, okay, since there is no external fragmentation between frame pages, okay. So and it is also a non-contiguous programs. I mean locations. Sorry. So storing programs in non-contiguous locations. So the memory is used for more efficiently because empty page frame can be used by any page of any job. So you can actually divide the page equally. All right. So you in this scheme, okay, you determine the number of pages, you locate enough empty page frames in main memory, and then you load the pages. Okay, so not necessarily contiguously. Okay, so but the thing is that when you have that, okay, when you divided the pages into equal size, okay, you need to have a table to be referred to. All right, so because you want to keep track of the pages of the programs that you have divided before. So this one will increases the size. Okay, so increases the size in terms of the tables that you need to manage in order to keep track of the pages. So there are going to be 3 tables, okay, to keep track of the pages. So you're going to have JT, PMT, and MMT. So job table, page map table, and memory map table. So that would somehow give some kind of complexity to the OS, okay, in order to operate, okay, under this scheme, okay. All right, so I think this one is quite straightforward. Okay, so just go through this one. Okay, page map. Okay, so and then the second one is demand paging. Okay, demand paging where you actually load only part of the program into memory for processing. Again, is equally sized pages, okay, divided into equally sized pages, the same as the previous one. So when the job runs, okay, pages are brought into memory as needed. So it allows a user to run jobs with less main memory. So in this scheme, okay, you also need a few tables, if I'm not mistaken. 3 tables, is it? Where is the table? Oh no, okay, not this one. Yes, okay. Okay, so you still need tables to actually to refer to the process, okay, and also the page frame number and so on. Okay, so but in this demand paging, okay, what's different is that it requires high-speed direct access storage. Okay, because you're going to pass the informations to secondary storage. Okay, so when you run the programs, okay, so you actually the page must be passed quickly from secondary storage to main memory and back again. So that's here, going there and here, okay, from the main memory to secondary storage. So that's different from the previous one. So so how and when these pages are swapped depends depends on the policies. So they come up with some kind of policies to let the process run, okay, smoothly, right? So for demand paging, it needs high-speed direct access storage, okay, and also they're also referring to the page map table, okay. So they will check for, okay, whether it's already in memory, okay. So for the page frame number, so is it already in memory, or contents have been modified or not, and has been referenced recently or not. So they have to check for that, okay, in order to proceed with the process, okay. So that's for demand paging, okay. So, okay, and then so page replacement policies and concepts, okay, there are 2 policies for this one, 2 popular policies, first in, first out, and also LRU, least recently used. Okay, so you have done the the lab work. Okay, so I believe you understand very well about this one, about this concept of FIFO and LRU. Okay, for the page replacement policy. So this is how you actually first in first out. I think this one is very straightforward. So you should know how to actually count how many interrupts, what's the percentage of interrupts for the failure rate is how many percent, and also the success rate is how many percent. Okay, so this one is for the page replacement policies. Okay, so as LRU, least recently used, okay, where you swap out the pages that show the least amount of recent activity based on the assumption that these pages are the least likely to be used again in the immediate future. Okay, so that's the concept of LRU. Okay, so again, you need to know how to calculate the failure rate and the success rate, okay, for this one. Okay, so another variation of this LRU, there is a clock page replacement policy. So for this clock page, and then another one is bit. Another one is, okay, LRU uses an 8-bit reference, okay, bit shifting technique to track the usage of pages in memory. Okay, so when a page is first copied into memory, the leftmost bit is set to 1, so remaining bits are set to 0. So at each time when it changes, okay, the memory manager will shift every page reference byte to the right by 1. Okay, so and each time a page is referenced, the leftmost bit is set to 1. So it keeps shifting, okay, to the leftmost bit, okay, when a page is referenced. Okay, so it's shifting. Okay, this one is this recently used. And then, okay, the mechanics of paging. So the information, specific informations about each page in memory in order to swap pages out. Okay, so there are a few mechanisms, okay, in order to do the swapping process. Okay, so let's say, so it's based on the cases. Where is the case just now? Okay, it's either case 1, case 2, or case 3, or case 4. So it's based on that. Okay, it's either is modified or not, or reference or not. Okay, so that kind of things. Okay, so it's based on the map table provided. Okay, so for the working set, okay, a failure to find page in memory is called a page fault. Okay, so the working set of a job is the set of pages residing in memory that can be accessed directly without incurring a page fault. So that's the working set without a fault. Okay, so that's working set means. Okay, and then there are 2 issues regarding working set. Okay, so it's either how many pages comprise the working set, or what is the maximum number of pages the OS allow for a working set. Okay, so for how many pages comprise the working set, it actually depends. So it's difficult to determine, okay, how many pages. So it depends on your programs, okay, and how complicated is it. Okay, so the maximum number of pages the OS allow for a working set. So this one, okay, it also depends on the program that you run. Okay, so the solutions is begin by identifying a job working set and then loading them into memory and in its entirely before allowing execution to begin, meaning that before the OS start, okay, they need to determine first, okay, how many pages needed, okay, and then for how long for each job is going to be executed. So that's the planning before, okay, the program's being executed. All right, so that's the working set. Okay. Okay, so the advantages of this demand paging, okay, so it actually introduced the concept of virtual memory. So I mean, the jobs are no longer constrained by the size of the physical memory. So you can actually, I mean, to reside somewhere else as if it was in your main memory. So memory is utilized more efficiently because sections of a job that are seldom used or not at all are not loaded into memory unless they are requested. So you are actually fully utilize the memory. Okay. But somehow, okay, for demand paging, it increased overhead, okay, caused by the tables and page interrupts. Okay, so remember how many tables just now? We have 3 tables, right, needed. So, and then it needs to regularly check the tables, okay, and then it has to go from the main memory to secondary storage and so on, okay. It was like a cache memory. So you have to check whether it was already in memory or not, okay, and so on, okay, the process going on. Okay, next is segmented memory allocation. Okay, so each job is divided into segments of different sizes. So one for each module that contains pieces that perform related functions. Okay, so you divide it into modules. All right, so this approach reduced page faults that resulted from having a segment's loop split over 2 or more pages. Okay, so trying to, help to solve the problem of looping, okay, and so on in your programs. So main memory is not divided into page frames, okay, but memory is allocated dynamically according to your modules. Okay, so let's say you have a main program here, okay, with 349 lines of your program. So it is divided dynamically according to the size of your programs. Okay. Okay, so, and then each segment is numbered and a segment map table is generated for each job. Okay, so there is going to be a segment map table for each job. So SMT contains the segment numbers, segment length, access right, status, and its location in memory when it's loaded, okay, by the program. So it's also containing reference, modified, and status bits. Okay, just like in demand paging concept. So again, you have 3 tables in this approach, okay. Okay, so we'll just go through this one. Okay, the difference between paging and segmentations, okay. So pages are physical units that are invisible to the users, okay, program and of fixed size, but segments are logical units that are visible to the user's program and of variable sizes according to the user requirements, okay. So, and the last schemes is segmented or demand page memory allocations. So it's actually a combination of these 2 techniques, okay, segmentation and demand pages. But okay, it was chosen accordingly, okay, offers a, so if you need, if it's better to have segmented, then it's going to apply segmented, okay. If it's better to have demand, then they will use demand page memory allocation. So it offers the logical benefits of segmentation, okay, and also the physical benefits of paging. So it's a 2 ways approach, okay. So this will help overcome the problem of segmentation, such as compactions, okay. In segmentations, they need to do compactions, and then there is also external fragmentation and also secondary storage handling, okay. Okay, but in this approach, you need 4 tables. All right, job table, segment map table, page map table, and also memory map table. Okay, so there is going to be 4 tables in here. Okay, so this one. Okay, major disadvantages. Okay, overhead required for extra tables. Okay, extra 1 more tables, okay, and then time required to reference this SMT and PMT, okay. So in order to solve this problem, okay, there is they provide solutions called associative memory, which is used to minimize the number of references and speed up the process in segmented or demand page memory allocations. So this is actually the solutions of it, associative memory. Okay, so it's a set of registers allocated to each active job, okay, reside in main memory, and the number of registers varies between systems. So accordingly, okay, according to your jobs, according to your system, and so on. Okay. Okay, so to the CPU, SMT. Okay, so this, I think this one, you can read through this one, okay? This is how it works, I think, all right? But the thing is that, okay, because you all, in this approach, okay, the system need always to access SMT and PMT, so it's going to be time consuming, all right? That's why it's incurred more overhead. Okay, so this associative memory overcomes this drawback, okay, by storing information about the most recently used pages in memory. So you can directly access to that, okay, instead of searching it throughout the tables. All right, so it become more easier. Okay, thank you. So okay, then. Okay, this is how it works. Okay, when a page request is issued, two searches are initiated through SMT and PMT, and also through the content of associative registers. Okay. Okay, so the virtual memory, so okay, makes it possible to swap pages between main memory and secondary storage. Okay, so given the right schemes, okay, that will be used, okay, so it's actually given advantages of using virtual memory. So it gives the user the impression that the entire program is loaded in main memory. Okay, when actually is only a portion of the program is loaded into your main memory. Okay, so prior to virtual memory, programmers are responsible for making sure program fits into available memory. So it depends on your programs. Okay, so you can the programmers can divide their programs into section or segments. Okay, nowadays we called it as overlays. Okay, and also the program could begin with only the first overlay loaded into memory, not all of it. Okay, so as the first section nears completion, okay, it will instruct the system to lay the second section of code over the first section already in memory. So the process continues until the program finishes. Okay. Okay, so these are the differences between virtual memory with paging and virtual memory with segmentation. So as you can see here, okay, paging allows internal fragmentation within page frame, okay, but not, but okay, for virtual memory with segmentation, okay, it doesn't allow internal fragmentation. Okay, wait there. All right, so and then doesn't allow external fragmentation for paging and allows external fragmentation with segmentation. Okay, and both are actually okay, is with paging, okay, programs are divided into equal size pages, but segmentation, remember, it was dynamically, okay, the size of it was dynamically divided, okay, that's result into unequal size of segments, okay, because it was according to the modules, okay, and then absolute address calculated using page number and displacement, and also for segmentation, absolute address calculated using segment number and displacement. So in virtual memory with paging, it requires PMT, and segmentation, it requires SMT. Okay, so you can read through this one. I think this one is very straightforward. Okay. Okay, so and another thing is that segmentation allows users to share program code. Okay, so you can actually share the program code. A shared segment contains an area where unchangeable code is stored and also several data areas, one for each user. Okay. Okay, so I think virtual memory involves, so this one you can actually go through on your own. Okay, can read the advantages of it. Okay, eliminates external fragmentation and minimize internal fragmentation, allows sharing of code and data, facilitates linking of program segments. Okay, because you have a module and then you can link between chapter 3. Any question on chapter 3?
So in this segmented demand page location, essentially it splits, like it first takes a job, then splits it into different segments, and then each segment will be split into pages. Is that how it is?
They don't call it pages, they call it segments. All right, so it was like a pages lah, okay, but it is called segments because it's based on modules. They don't call, because in, let's say, okay, in pages, okay, what you do is that you divided the thing equally according to the size, right? And then you divide. So it doesn't matter whether you have, let's say, in your programs, let's say you have a main programs, right? And then you have functions, right? Subroutines, routines, right? Things like that. Okay. So in pages, we don't count that. Okay. So they don't separate that according to your modules in your programs. Okay. But in segmentation, okay, they divide that in according to your modules. So let's say your main programs is the size is, let's say, 500 kilobytes, and then there is another modules, okay, which is a subroutine of your programs. The main program is, the size is about 50K. So it will divide it according to the size of that program, and a small program things. Okay, but in pages, no. All right, so it will divide it according to the size that you fix on the pages. So it doesn't matter whether it includes all of the main program or not. Okay, so it doesn't matter about that.
Okay.
Okay, is that clear? All right. Okay. Any other questions before we move on to chapter 4? No. All right. So I'll go to chapter 4. Okay, chapter 4. Okay, so in this chapter, okay, so you have some terms, okay, in this chapter. Process, okay, is what is process, what is thread, and what is a processor. Okay, so process, an active entity that requires a set of resources, okay, including a processor and special registers to perform its functions, and also called the task. Okay, so that's the whole thing is called a process. And then for thread is a portion of process that can run independently. Okay, it's a portion of that process, but it can run independently. All right, so that's thread. And then processor, also known as the CPU. It's part of the machine that performs the calculations and execute the programs, execute the algorithms, and so on. So that kind of things. So that is processor. Okay, so analogy is this one. I think you can read through this one. Is very straightforward. You can. I think this one is very easy to understand, right? So you have give you an analogy. Okay, what is let's say you buy a bookshelf and then you get home. Okay, you take out the instruction manual and start to read the instructions and how to assemble. And while doing that, okay, while following the steps, and then there's an interruptions, okay, from in here, from your brother crying and so on. So you can read through this one, but okay, this one is interesting. Okay, compare that to the OS. Okay, you can compare that to the OS in order to understand better what is processor, what is programs, okay, what is process and interrupt and so on. Okay, so you are acting as the processor, okay, because you're the one who processes everything. Okay, and then there are two programs, okay, assembling a bookshelf bookshelf and also bandaging your brother's injury, job A and job B, right? So when you're following the instructions to assemble the bookshelf, so each step you perform is a process, okay? Each step that you followed is a process. So your brother's cry was an interrupt to your process. Okay, so when you left your bookshelf to treat your brother, so you left for a higher priority programs. Okay, so when you are interrupted, you perform your context switch, meaning that you mark where you stopped just now. Okay, so that it's easy for you to come back later and continue with the job that you left before. And then when you are treating your brother, so each step, okay, again, each step you execute is a process. And when a job is completed, it's finished or terminated. Okay, so by comparing this, I think you have a very clear, right, clear definitions on what is it, okay? What is the terms refer to, okay? So, okay, so in multi-programming environment, okay, why is that we need all those, and I mean, why you need to understand all those terms? Because we are going to learn about multi-programming. So in multi-programming environment, okay, so they're going to have many users, many jobs, okay, and then the processor must be allocated to each job fairly and efficiently, okay, so that we want to avoid what you have learned, deadlock, right? Remember, you want to avoid deadlock, any failure, okay, in your programs and so on. So this multi-programming requires that the processor be allocated to each job or process for a period of time and deallocated, okay, back when the period expires so that another program can make use of it. Okay, so in order to do this, you need some kind of algorithms, you need some kind of policy or scheduling, okay, scheduling policies in order to implement this. Okay, that's why in multi-programming, there's an approach, okay, of scheduling policies, okay? So because one processor can be shared by several jobs or processors if and only if the OS has a scheduling policy and scheduling algorithm, okay, to determine when to stop working on one job and proceed to another. So, okay, so it's very clear here, right? Okay, in order to solve the problems of multi-programming, okay, so that's why we need the policies or the scheduling. Okay, so here, okay, the manager that in charge is processor. So it composed of two sub-managers, which is a job scheduler and also process scheduler. All right, so I think the most common one is first come, first serve. All right, so this one is, I think all of you know about this one. So in, okay, job scheduling versus process scheduling, okay, so each job is initiated by the job scheduler based on certain criteria. Okay, so once job is selected for execution, the job scheduler determines when each step or set of steps is executed, which is also based on certain criteria. Okay, okay, so let's go through. Okay, this one I think you can read on your own. Okay, how they actually choose. Okay, so other responsibilities decides when a job should be interrupted. Okay, this one I think Saida mentioned already. I have mentioned about this one. Okay, so job, okay, job and process status. You have this from hold to ready, ready to running, running to ready. So these are the transition in process scheduler, running to waiting, waiting to ready, and running to finish. That's the process of the whole things. Okay, so this one boleh baca lah. Okay, this one is straightforward. So in process scheduler, each process is represented by a process control block. So it contains basic information about the job. Okay, what is it? Where is it going? Okay, how much processing has been completed, and where does it start, and how much it has been spent. Okay, in using resources. Okay, so you can read the details here. Okay, I want to go to the. Okay, what is good? about the process scheduling policy. You can actually maximize the throughput, minimize response time, minimize turnaround time, minimize waiting time, maximize CPU efficiency, ensure fairness for all jobs. Okay, so when the job criteria is meet up, so you can actually okay fully utilize the process, fully utilize the memory. All right, so this one. So there are 6 process scheduling algorithms. So I believe that Dr. Seidel has already explained to you how it works in details, right? So you have done also your programming parts for lab work. Okay, for yours is which one you buat hari tu? Shortest job next, is it? And also first come first serve. All right. So you have first come first serve, shortest job next, priority scheduling, shortest remaining time, round robin, and multi-level queues. Okay, so first come first serve, I think all of you, it's not a problem to understand this one. Okay, first come first serve. Okay, straightforward. Okay, so this one is a non-preemptive. Okay, so what does non-preemptive means is that once a job is being executed, okay, you cannot change the job to another job. Okay, so it means that you have to finish the job first, okay, before you proceed with the next job. So let's say you have job 1, job 2. So when you start running the job 1 first, because it's come first, okay, you have to finish job 1 first. So you cannot stop in the middle and then let job 2 continue. No, you have to finish job 1 first, then only you can proceed with job 2. So that's what non-preemptive means. Okay, so very simple, this one, implemented using first in first out queue. All right, so it's good for batch system, okay, but not for interactive system. Okay, so because we want quick response time. Okay, so this one is very straightforward. I think you understand this one, right? So timeline for the job sequence ABC using first come first serve. Okay, it continues, it will run the job according to the who comes first. Okay, let's say this one, okay, the sequence is ABC, so A will go first. So you have to finish A first, even though at you have a shortest job coming. Okay, so but you still need to finish job A first, and then continue with job B and C. So you have to follow the sequence A, B, and C. So you cannot stop in the middle. So okay, the turnaround time. Okay, I think this one also you know how to calculate it, right? So it's 15 plus 17. Okay, plus 18. So okay, okay, providing that okay the arrival time okay is about the same time. Okay, so if you're not given any arrival time, then you can calculate like this. Okay, meaning that 15 plus 17 plus 18 divided by 3. Okay, but if there is an arrival time, okay, then okay, you have to minus with the arrival time. 15 minus the arrival time, plus 17 minus arrival time, and also 18, and all the sum okay divided by 3. All right, so this one is first come first serve. Okay, all right, so okay, let's see the difference here. Let's say the job C start first. Job C, the sequence is C arrive. Okay, C arrive first, and then B, and then A. Okay, so the sequence is C, B, A. So you can see a very huge difference in terms of the turnaround time here. Okay, so you can see this one is 16.67 and this one is 7.3. See the difference, okay, between it. So it's not that practical, okay, actually for first come first serve, all right, to be implemented, because the disadvantage of this, okay, policy or scheduling algorithm is that the average turnaround time vary widely and are seldom minimized. Okay, because you have to follow the queue. Follow the sequence. Okay, you cannot interrupt in between because it's non-preemptive. Okay, Okay, next. Shortest job next. Okay, or sometimes in some other books might call it as shortest job first. It's the same thing. Okay, so this one is a non-preemptive, meaning that you can stop in the middle. Okay, sorry. Non-preemptive means that, okay, sorry. Non-preemptive means you cannot stop. Okay, once the job being executed, okay, you have to proceed with the job until it finish. Then only you can proceed with the next one. Okay, for this one, for this policy, you have to. This one is going to be very. It's going to be very practical and effective if, okay, if the arrival time is about the same time. Okay, but if you have a different times, then it's going to be like a first come first serve. All right, so for this one to happen, to use this scheduling policy, okay, the arrival time must be at about the same time. Okay, then it's practical to do this one. Okay, so shortest job first. Okay, let's say, okay, the job, okay, follows this. You have the jobs, okay, A, B, C, and D. All right, and it arrives at the same time. Okay, A, B, C, and D. So you can choose. Okay, you can choose. Okay, B shortest. The shortest one is B, followed by D, A, and C. Okay, but if you were given, let's say, arrival time, then you need to look at the arrival time. Okay, you must always start with the one that start at time 0 first. Okay, if you are given the arrival time. If you're not given the arrival time, then it's okay. You can do this one. You just pick, okay, the shortest one and put it first on the first queue, and then followed by D, A, and C. But let's say it's given here, A arrive at, let's say D arrive at, or A, okay, A arrive at time 0. All right, okay. So you have to start with A first. So you need to finish A first, then only you look at the others. Which one is the shortest one? Then only you can proceed with that one. Okay, so that's for shortest job next. Okay, and then shortest job next. So the formula for the turnaround time, okay, is this. Okay, it's about the same time. Okay, SJN, okay, optimal. Okay, so here SJN is optimal only when all jobs are available at the same time. Okay, and CPU estimate are available and accurate. Okay, so it's optimal when all jobs are available at the same time. Okay, okay, priority scheduling. This one is non-preemptive algorithm again. A most common algorithm for batch systems. So it gives preferential treatment to important jobs. Let's say, okay, when you're running some programs, okay, there is some very important jobs need to be executed first with the highest priority. Okay, so this scheduling policy will take place. Okay, so it allows program with the highest priority to be processed first, and they are not interrupted until their CPU cycles are completed or a natural wait occurs. Okay, so this one is very, very straightforward. You just give to those who have a very high priority. Okay, but somehow, okay, it was determined. Okay, the priorities can also be determined by the process manager based on intrinsic characteristics such as let's say memory requirements. Okay, it's based on memory requirements, and then number and type of peripheral devices, total CPU time, amount of time already spent in the system. So okay, in order to avoid aging, okay, aging means the system waits for too long, okay, without having any without getting any chances to proceed. Okay, so here comes the priority scheduling. Okay, so it gives some priority to the process to proceed. Okay, and then shortest remaining time. This one is preemptive compared to the previous one. The previous two is non-preemptive. This one is preemptive, meaning that you can stop, okay, in between, okay, depending on the time allocated to the job. Okay, so the executing job can be preempted if a new job in the ready queue has a shorter completion time. So, okay, so you will always look at the arrival time. Okay, in this scheduling policy, you need to look at the arrival time, and then this one. Okay, arrival time, time 0. Okay, time 0. Okay, let's say job A arrive first. So okay, and then your okay, and also you do it one at the time. Okay, after you finish for one unit, and then you will look at time 1. Okay, whether other job has arrived. Okay, if not, you can continue, or else okay, you can calculate okay, what are the other remaining times that have the shortest one, so you will continue with that job. And then okay, the next round, okay, the next unit, the next time, again you look at the arrival time, and then what is the remaining remaining time left for the other jobs. Okay, and then you will do the one with the shortest remaining time first before you proceed. Okay, so average turnaround time, the calculation is the same for all the scheduling policy. Okay, so shortest remaining time. Okay, round robin. Okay, this one is based on time quantum given. Okay, time quantum, so it's based on time quantum, so you will calculate it. This one is also preemptive, so you calculate the job okay according to the time quantum given. Okay, but it cannot, but one problem with round robin is that it cannot be too short for the time. Where is it? Okay, if it's too short, sorry, if it's too large, okay, it becomes first come first serve. Okay, if it's too large, the time quantum, let's say you set the time, the system set the time quantum to be 10 seconds, so it's too large. Okay, when it's too large, it becomes first come first serve, because you will definitely complete that job first. Okay, with the probably okay, let's say you have the job with the maximum number cycle time is about let's say 8, but your time quantum is 10. See, okay, so you'll definitely process, okay, proceed with the one, okay, arrive first, okay, and then followed by the next one. Okay, so it will become first come first serve scheme. But if it's too small, then you keep switching. Okay, it will cause the system to keep switching between jobs, so it will actually slows down the job execution and increases the overhead dramatically. All right, so it cannot be too large or too small. So probably between 3 and 4 is just nice. Okay, the time quantum. Okay, time quantum, and then round robin, and the last one is multiple level queues. So this one is not a separate scheduling algorithm, so it works in conjunction with other schemes. So it could be a priority-based system with different queues for each priority level, and then a system with one queue for CPU-bound job and another for I/O-bound jobs. So the process scheduler will alternate between the two queues. So you have different queues for that. But okay, the scheduling algorithm will process based on the queues that provided. Okay, that has been set. Okay. Okay, so of course there are some issues. There are some issues in it. Okay, so some of the issues is the processor allocated to jobs in the first queue until it's empty before moving to the next queue, or does it travel from queue to queue? So there are some issues. Okay, you can read through this one. So these issues, okay, will be solved according to the case. Okay, if there is no movement between queues, okay, so what is going to be how is it going to be solved? Okay, the CPU is allocated to jobs in the high priority queue using FCFS. So those issues will be solved according to what case is that. Okay, so Case 1, no movement between queues. Okay, case 2, movement between queues. So, and then case 3, variable time quantum per queue. Okay, so, and case 4, if it's aging and how it's going to solve that. Okay, so that's for processor management chapter 4. Okay, all right, any question?
Doctor, can you explain the how to get the turnaround time in SRT?
In?
How do we know how to get turnaround time? Like how to get the order, and you know, like from the A B C B D A, how do we decide like which one is how A is first and then C B D in shortest remaining time? Shortest remaining time.
Shortest remaining time. Okay, so it's going to be when it's finished. When it was finished, so you will minus that time. Okay, minus from the time it finished. Okay, minus with the time it started.
So
for
if we
job.
Can we go to the SRT slide just to see?
SLT, yeah.
SRT.
SRT.
Shortest remaining time.
Okay, this one.
Yeah, the one where it shows this one, because if in the previous slide it shows how the ordering goes, and if it's from when it's first entered all the way to when it's finished, then shouldn't A technically be like 14 turnaround time?
Oh, this one.
Or am I getting no, the one below it?
This one?
The one below and both 44 and 45, both 44 and 45, like
44
both
and this one and
okay. Because
okay, job A, all right.
Because
okay, 6. Okay, minus arrival time is 0.
Because in 44 it shows A finishes last, unless I'm understanding.
Oh, right.
44.
Okay. 6 minus 0. Sorry, 10, 14. 6 minus 0 is 6. Then 3 CPU cycles is 3 average turnaround time. Oh, okay. Sorry, jap kena tengok balik juga ini. A is 14 minus 0. Okay, 14 minus 0. And then D is 9 minus arrival time is 5. So it's become 4. B 5 finish at 5 minus arrival time at 1 is 4. And then C is going 3 minus 2, 1. So you get 14 and then 4, 14, 4, 4 and 1. 14, 4, 4, 1. Is it? The same job problem using okay, this one is SJN, sorry. 14, 4, 1 and 6. Sorry, 14. Okay, job A is 14 minus, job A finish at 14, right? 14 minus arrival time is 0. Okay. And then job, this one is job A. Okay, so job A is 14 minus 0. Okay. And then job D is 9 minus arrival is 5. Okay, so 9 minus 5. And then job B is 5 minus 1. Okay, and then job C. Job C is 3 minus 2. Okay, so you'll get 14, 4, 4 and 1. 14, 4, 4, 1. 14, 4, 4. Oh, okay, there's some typo here. Okay, sorry. 14, 4, 4. Okay, according. Okay, I'll just write this one again, okay? Ada typo kat sini, sorry. Okay, thanks that you asked the question. Okay, so okay, can you calculate? We calculate again, all right? So 14 for A is 14 minus 0 arrival time, right? Okay, and then B plus. Okay, and then for B is 5 minus 1. 5 minus 1. Okay. Then C is 3 minus 2. 3 minus 2 plus, and D is 9 minus 5. Okay, 9 minus 5. Okay. Divided by 4. Okay. All right. So you calculate again this one. Okay. Okay. So that's how it calculated. Okay. Can.
Yeah. Also, Doctor, I think I may have misunderstood the slide. I thought this the one in slide 45 was also SRT. I may have misread it.
Right.
Don't worry about it.
Okay.
Okay, don't worry.
Right. So this one is SGN compared to SGN.
Okay,
right?
understand.
All right. Okay. Okay. So any other question?
Sorry, doctor. So this one is not subtracting it with the arrival time.
The
previous, just now, what you did.
What is it?
For 44.
44, okay.
Yeah. So there's a typo for that.
Oh yeah. Okay, sorry.
No, I mean, isn't it supposed to minus by the arrival time?
Yes. Supposed
because
to.
A, B, C, D is supposed to be 0, 1, 2, 3, right?
A, B?
A, B, C, D. Can you see the slide 45?
45, okay. This one is SGN.
Oh, 43, sorry.
43, okay, yes.
Yeah, the arrival time is 0, 1, 2, 3, right? So supposed to like.
Okay. Yes.
Yeah.
Yes, so, okay. So, okay, arrival time 0, 1, 2.
So supposed to be, I think the previous one is correct, right?
Yes. Okay. There is typo here. Sorry. Okay, so you need to refer to the arrival time, okay, 0, 1, 2, 3, this one, okay, and then you minus with that one, okay. You refer to the finished job here, okay, what time does it finished, and then you minus with the arrival time, okay. Sorry for the typo. Later I will make the corrections and upload again the slides, okay.
So that means job D has arrived at time 3, but it maintains at a ready state. So that means it's 9 minus 3.
9 minus. Okay. Job D arrive at. Yes. 9 minus 3. Yes. Okay.
Okay.
Yes, according to this one. Okay. Yeah. That's correct. Okay. Thanks. You asked the question. Sorry. Okay. All right. So anything else? No. Okay. So we shall go next to chapter 5. Okay, so chapter 5, this one, okay, this is where you learn about Banker's algorithm. Okay, remember you do the lab work. All right, so you learn about deadlock. Okay, I think this one is very straightforward. You know what is deadlock, right? You know what is starvations. Okay, so deadlock and starvation, I think this one you can read through this one. So there are 7 cases of deadlocks, okay. on file request databases, okay, dedicated device allocation, multiple device, spooling and discharging. So, okay, you can read through this one. I don't think you have a problem with this one. Because I want to share with you how actually you want to do how actually you want to do a calculation to determine whether is a safe state or is an unsafe state. Okay, so can you read this one on your own? I think because this one is very straightforward, right? Recovery methods. Okay, it tells you the method, what is starvations. Okay, Ken?
Okay.
All right, so I'll go through this one. Okay, let's see this one. Okay. Okay, so I have already uploaded this one, this exercise on how you're going to calculate whether you have a safe state or not. Okay, when you want to actually to allow or not to allow a resources. Okay, okay, when there is an addition to the resources, let's say. Okay, so okay, let's see this one. Okay, let's see, you have this one, resource vector is R1, R2, and R3. Okay, you have 9, 3, and 6. Can you see my page?
Yes.
All right. Okay, glad that you can start. Okay, let's see. You have R1, R2, and R3. You have 9, 3, and 6. Okay, and then, okay, so we want to determine whether this one is a safe state or not. Okay, so you were given a resource vector R, okay, R1, R2, and R3. So each is 9, 3, and 6. And then you're given claim matrix. Okay, claim matrix by process P1, P2, P3, and P4. Let's say you have P4 process. Okay, so P1, P2, P3, and P4. Okay, so they claim to have, okay, 3 R1, 2 R2, and 2 R3, and so on. Okay, so this is the number of claim matrix for the process according to the resource. Okay, and then the allocation matrix. Okay, allocation matrix is means that the number of resources allocated to each process. So it definitely not all the resources has been allocated to the process. So you can see here the matrix is P1, P2, P3, P4, okay, 1, 0, 0, 6, 1, 2, 2, 1, 1, and 0, 0, 2 has been allocated accordingly, right? So you need to calculate the need matrix, okay? How many more that you need for each process. So, okay, so first, you total up this one first, okay, R1, okay, so R1, the total is 6 plus 1 plus 2. So it's 9 here, right? Okay, and then this one is 2. You total up, okay? R3 is 5. Okay, so, and then this one is need matrix. So need matrix, how do you get this one? Sorry. How do you get this one is that you minus C minus A. So claim matrix minus with the allocation matrix. So you know how many more you need for that particular process. Okay, so you minus that one. So 3 minus 1 is 2 here. 2 minus 0 is 2. 2 minus 0 is 2 here. So you do the rest. Okay, 6 minus 6 is 0. Okay, 1 minus 1 is 0. 3 minus 2 is 1. Okay, and then you have this one. 3 minus 2 is 1. Okay, 1 minus 1 is 0. And 4 minus 1 is 3. Okay, and then this one, 4 minus 0 is 4. 2, and this one is 2 minus 2 is 0. Okay, so did you get it? All right, so and then the resource vector, the initial resource vector is 9, 3, and 6, right? So the total allocated resources, okay, is 9, this one, okay, 9, 2, 5, okay, 9, 2, and 5. So how do you know what is your available vector for the resources? Okay, so the available vector is you minus that one. So 9 minus 9 is 0. Okay, 3 minus 2 is 1, and 6 minus 5 is 1. Okay, so with the amount of available vector, okay, 0, 1, 1, can P1 actually proceed? Can P1 proceed?
Nope.
No, right? So it goes to the next one. So can P2 proceed?
Yes.
Yes, okay. So P2 will proceed. Okay, proceed first because the available vector is 0, 1, 1. So P2 will actually complete the job, right? Okay, so P2 will complete the job. Okay, so after P2 complete, meaning that there is no more claim matrix here. Okay, so you can simply put this one here. This one is done, meaning that the job is done. Okay, so done. 0, 0, 2 is done. Okay, so again, you do the same things. Okay, so now, okay, 3 to 2, okay, minus 1, 0, 0. Okay, you calculate again for your resource vector. Okay, okay, so 3 minus 1 is 2. Okay, this one is 2 minus 2, okay, 2. And then you have the rest of it, okay, which is 10342, okay. And this one is 4. Sorry, 0. 4 to 0. Then you calculate again this one. So this one will become 3. This one will become 1. This one will become 3. Okay. All right. So resource vector is 9, 3, 6. The actual one. So total allocated resource now is 3, 1, 3. So you have the available vector is 9 minus 3 is 6, 2, and 3. Okay, so with the amount of available vector, okay, can P1 proceed again to complete the task?
Yes.
All right, okay. So P1 can proceed. Now P1 can proceed means that P1, okay, proceed means P1 complete the job. So you put this one here, 0, 0, 0. So you're done with this one. Okay. Okay, so then you calculate again. So this one, the total allocation matrix is, this one is 2, 1, and 3. So this one you calculate again. This one is 103, right? 103, 420. 103 and 420. Okay, so again 936 here. Okay, so this one is 2, 1, and 3. So your available vector now is 9 minus 2 is 7. 3 minus 1 is 2. Okay, 6 minus 3 is 3. Okay, now can we proceed with P3?
Yes.
All right, okay, so you can proceed with P3, so the process continues, okay? So I think this one, you get this one already. This one we still have 4, 2, 0. Okay, so your total here is going to be 0 here, 0 here, and we have 2 here. Okay, so this one is 936. Okay, so allocated resources is 0, 0, 2. So your available vector is 9, 3, All right. So the last one, P4. Can P4 finish the job?
Yes.
So is there any deadlock?
No.
No, okay, because you can just proceed, all the process can proceed and finish the job accordingly, right? So there is no deadlock. So this one is considered as a safe state, meaning that all the process is done, okay, accordingly. So it's a safe state, okay? So can run complete, no possibility of having deadlock, all right? So that's it. So now let's say, how are you going to show the available working arrays changes as each process terminates? And so you just calculate it, okay? So we need just add on, okay? So initial state available vector is 0, 1, 1, okay? And then the next available process to proceed is P2, and then P2 returns 612, so you just add 612 plus 0, 1, 1, so you'll get this one, 6, 2, 3. This is how you come up with the available vector, okay? And then to 623P1 complete, so you return 100, so you add on another 100, so this one is going to be 7, 2, and 3, right? And then you add 2, 1, 1, okay? So this one is going to be 9, 3, and 4, okay? And finally it's 9. You should get the exact one, the initial resource vector 936, okay? So meaning that your working array is correct, okay? So it's done, okay? So how are we going to determine whether it's safe or unsafe, okay? Okay, so let's say you have the same thing, okay? You have the same resource vector, and then claim matrix, allocation matrix, and need matrix. So if there is, let's say there is a request of 101 from P1 arrives. So you want to know whether you should proceed with the request, to grant the request or not. Okay, and then you want to determine whether is it safe to proceed with the request or is it not safe to proceed with the request. So what you're going to do is actually you do the same thing, okay? So what you do is that, okay, you calculate again. So the same process, okay? So now there is a request, let's say you grant, okay? So to test whether it's safe or not, so you have to assume that the request is granted and you do the followings, okay? The same thing, just like the previous one. So what you do is that you plus 1, okay? For P1 request another 1 for R1 and another 1 for R3. So you're going to get some add-ons here, okay? So 3 to 2, okay, so this one minus claim matrix minus allocation matrix, okay? So 3 minus 2, this one is going to be 1. 2 minus 0 is 0, 2. And then, okay, 2 minus 1 is 1. Okay, so this one is 1. Okay, 0. 3 minus is 2. All right. 1, 1. Okay, 3. Okay, 2. 3 minus 2 is 1. 0. And 3. This one is 4. 2 and 0. Okay, so you total up this one. This one is going to be 2, 5, 2, 7, 8, 9. So this one's going to be 9. Sorry, this one is going to be 2, and this one is going to be 5. 9, 2, 5. All right, so this one is 9, 3, 6. So the 9, 2, 5. 9, 2, 5. So what is your available vector now? Is 0, 1. Okay. Okay, so 0, 1, 1. Okay, so with 0, 1, 1 available vector, can you proceed with any process in the queue?
to add process 3?
Is it possible to proceed with any process in the queue?
No.
No, right? So is it actually safe to grant the access to add on the resources or not?
No.
Okay, so it means that it's not safe to proceed with it. Okay, it's not safe to grant the P1 request, okay, to add on the resources here. Okay, if the request 101, okay, arrive from P1, okay, so you should not proceed. The system should not proceed. If proceeds, then it'll cause a deadlock because cannot proceed with any of the process. Okay, so will it be safe or an unsafe state? So this is what we call unsafe state. Okay, unsafe. So this is how you determine whether it's safe or not. Okay, so that's it. Do you have any questions?
Sorry, Doctor.
Mm-hmm.
May I know the flow for the process? Supposed to be 1, 2, 3, 4, or for example, for the first example, right? Just now we have finished the process 2. We allocated process 2, and then it goes back to process 1. Or is it supposed to continue with process 3, process 4, and then only it goes back to process 1?
No, because it's actually based on the queue. Okay, so it always goes to the one that what we call that not exactly was like you must, okay, because you must follow the sequence, okay, and then okay, let's say P1, P2, P3 and P4, right? Okay, and but because you cannot proceed with P1, okay, you proceed with P2, okay, then you must always go back to the previous one which is not completed yet.
Okay, all right.
Okay.
All right. Thank you.
All right. Okay, so any other questions? No. All right, so I think that's all for our revision class. Okay, anything else? No.
No.
All right, so I wish you all the best for next week mid-semester exam.
I know. How many questions do we have?
How many questions? I can't remember. I think, is it probably, I'm not sure. I'm not sure, and I'll check again. Okay, I think about is it 30 questions? Maybe about 30 questions.
All right, thank you, Doctor.
Okay, you just follow you just read the notes and you should be able to answer the questions. Okay, any more questions? You can always ask questions if you anything that you don't understand through the chat functions that we have provided on the Spectrum. Remember, okay, when you go to Spectrum, there is a section for chat there. You can ask questions there. Okay, everyone, thank you for attending the class today. Okay, all the best.
Thank you, Doctor.